Joan, are you recording? Okay. So so now we're going to get into the core of the course, which is stats review and association studies. Okay, so we're going to learn some stuff. I have to warn you that today's class is going to be a lot of statistics. Okay, and I know that if there's anything that computer science students hate more than math, it's statistics. Okay, so please, but I will teach you all you need to know, and bear with me. These concepts will be pretty easy. And actually, another thing I want to point out is that I am giving extra credit to anybody who emails me with typos that you find in the slides. Okay, and just now I noticed that this was saying March 29th. Okay, so I fixed it, but in principle, you could have gotten extra credit for that. And that even applies if you're watching this on video. Okay, so let's talk about statistics, okay? And we're going to be talking about something called hypothesis testing, and the goal of this area, of this whole problem, is we're going to want to try to answer a question by collecting data, okay? And so, for example, in the general population, 25% of people stay up until 2 a.m. every day, okay? So the question is, do computer scientists stay up later or late, okay? So we're going to collect data from class, right? So how many people here stay up until 2 a.m. every day? Okay, that's not bad, not bad, not bad. Coffee you won't admit, but I guess those things might be related, right? Okay, so let's say there's a total number of students of 80 in this class, okay? And let's say that the number that stay up late is 40, okay? So the question is, what does that tell you? Does that prove, like what would you conclude from that? So what would you expect to see in the population if the people in the class were the same? Yes? Well, yeah, that's a great question. But what I said is that are the people, computer scientists, the same as the general population? Okay, yeah, exactly. So you're right. How you define exactly what your question is, it could also be problematic. But now I'm just saying that, are you guys just like the average in the population? Okay, it would be more informative if I said, if I told you the double E students are this, and then are you different, right? But okay, but so there's 40. How many would I expect? Huh? 20. Very good, very good. And so the question is 40. So is 40 more than 20? Yeah, right. Is it a lot more or is it a little bit more, right? Okay, sounds like maybe it is more, right? What if it was, what if I observed 26? Or what if I observed 22? Is that a lot or no, right? So you can see, imagine that 40 maybe yes, 20 maybe no, right? 21 maybe no. So the question is, how do we compute this? And so that's what we basically do. So this is how we do this. This is kind of what's called hypothesis testing. What you do is you first assume that there's no effect, okay? So you're assuming that the people in the class are the same as if they would be, just in the general population. So then you compute the quantity of interest. The quantity of interest is basically what you compute in the data, okay? What is here you would say how many people stay up late, okay? That would be 40. So then here's the key thing. You transform the quantity to a distribution, okay? We'll talk about that step. So that way you transform the quantity into something a distribution that you know how it behaves, and then we'll use that distribution to measure the significance. Okay, so these last two steps we'll kind of go over. So let's go through this example. Okay, so the total number of students is 80. The number that stay up late is 40. Is this significant? So assume that the true frequency in the class is 0.25. So there's no effect. So that means that okay, so the observed frequency in the class is 0.5. That's the quantity of interest, right? So we assume 0.25, we see 0.5. Okay. So the question is, okay, so then the statistic, this is the transform the data into distribution. This is called the z-score. And I know this probably comes at you out of nowhere, but we'll talk about how we came up with this. But basically, the z-score is you take the true observation, you subtract it from the whatever you think the true frequency is, and you divide it by something, and then you get a number, okay? And then this number, basically you know that if it's greater than 2, then it's significant, and if it's not greater than 2, if it's basically between 2 and -2, then it's not significant, okay? And so these last two steps kind of might seem like magic, but this is the general concept, okay? So the key step, but this is always you're following these 4 steps. You assume that there's no effect, right? Then you look at what you observe. Then you transform what you observe into the statistic, and then you measure significance. Okay, so here, what about on the other hand? Let's say you had 800 students, and 250 of them stay up late. Okay, so then if I plugged into the same formula, I would get a 4.08. Is that significant? Yeah. Okay, but I'm looking at, look, now it's only 25 out of 80, right? So it's much closer to 20%, right? What about if this was, okay, so we're going to talk about this. So this is the basic idea, okay? We're going to talk about how we do this in a second, but in order to do that, I'm going to just kind of review a bunch of probability concepts and just review and kind of statistics. So in theory, all of you should have taken stats 100A or biostats 100A or whatever. But I know some people didn't, some don't. Or if you were in those classes, you didn't pay attention, that's fine too. What I'm going to do is I'm going to try to cover all the material that we need for statistics in class. So it'll be more challenging if you didn't take it, but please cover it, okay? So in general, this is the notation I'm going to use. I'm going to say event A occurs with some probability PA, okay? So if PA is the probability that event A occurs, what's the probability that the event doesn't occur? 1 minus PA, that's really good. It's right on the next line, okay? What about PB, right? B with PB, 1 minus PB, okay? The events that A and B both occur, okay, that's PAB, okay, right? What if they're independent? What's the probability of PAB? PA times PB, right? Okay, very good. And then what about this one? Probability of event A occurring given that event B occurred. Okay? I'm using this notation, P of A given B. Okay? There's other notations you can use, but works fine. It's the probability that both occur divided by PB. Okay? That should be familiar, right, from that. Okay? Bayes rule. People heard of Bayes rule? Okay. Do you know who this guy is? I mean, obviously he's Bayes, right? But do you guys know the whole story and all that stuff, right? No? Okay. Well, Wikipedia. Okay. I used to tell the story, but now just look it up on Wikipedia. Okay. But Bayes rule is a really simple rule, but it's actually the basis of a lot of probability theory, and it's particularly inference from data. Okay. So what is this rule that what is it? P of A given B equals PAB divided by PB, right? What is that? That's the conditional probability, okay? What about the second line here? What is that? What's the difference between the first and the second line? So there's a probability that A occurs given that B occurs, right? There's a probability that B occurs given that A occurs, okay? Now look at those two formulas. What do they share in common? This PAB, right? So if I solve for those, okay, I get that PB times P of A given B equals PB given A times P of A. And so then I can relate P of A given B in terms of P of B given A, and then multiplying and dividing by these guys. Okay, so this is the whole proof of Bayes' theorem. Okay, Bayes' rule. Okay, that's the basic idea. This lets you reverse the direction of a conditional probability, and you will see we'll be doing that a lot. Why will we be doing that a lot? Because in general, we're gonna measure data, and we're gonna want to find out about, like, disease. Okay, that's what we're gonna want to find out. So we're gonna be measuring data, and we're gonna want to find out about, like, our hypothesis or knowledge, right? But that's actually very hard to compute. It's actually much easier to compute if you assume that you know about the disease. What's the probability of observing the data that you observe, right? So this is very important because it lets you reverse the directionality conditionals, and so we'll see that a lot in the class. Okay, so now the other thing is normal distribution. It's defined by two parameters, a mean and a variance. If x is a random variable with mean mu and variance sigma squared, we denote this as, this is the notation we use, x, this little tilde, normally distributed, mean mu, variance sigma squared. Okay, so there's something called the central limit theorem, okay, which says roughly if you have an average or a sum of a large number of observations, it approximately follows the normal distribution. Okay, this is not really what the central limit theorem is. So if you have any colleague, or please don't tell my colleagues in statistics that this is how I defined it for you, but this is rough from what we need. This is roughly what we need. Okay, so the idea is that if you're computing averages over very large data sets, we can assume things are normal. For example, we're going to be looking at very large sets of SNPs. So SNPs are even discrete. Either you have it or you don't. But when you're averaging them, like looking at frequencies, basically they follow normal. So that's why this is important. Why we mostly look at normal distributions. Okay, so this is actually the definition of normal. This is the PDF. This is the CDF. Okay, this here is called the standard normal CDF. Okay, the standard normal is defined by phi, and it's basically the normally distributed with mean 0, variance of 1. That's what we'll be using a lot. Okay, so this is actually another picture of the normal distribution. This blue line is what? Huh? The what? The normal, yeah, it's normal, yeah, but it's the what? PDF, right? It's a PDF, right? And then the area of the curve, let's say this whole white region, what is that? That's the CDF, right? Okay, very good. And then this is like, the mean is mu. These are like standard deviations, okay, et cetera, right? Okay, so then the normal distribution for hypothesis testing, okay, here is, this is what's called the critical region, okay, typically. So this is like the standard bell curve, okay? So do you guys remember this one? Didn't you, in like high school, did you guys grades on this? You guys get, or like when you take your other classes, how do they set the grade? Like the mean is what? So like in my class, for example, the mean, like a C plus is going to be right here, right, when I take all your grades. And then, no, I'm just kidding, right? It's not going to happen, right? Like a C plus is like down here, right? Because we have grade inflation. What can we do about it? But anyway, yeah. But practically, okay, the idea is that this, right? If you've got something, this is called the critical region, which is out in these tails, okay? If your data's in these tails, right, then this is, you would call it significant, okay? So the tails are defined by the probability that's going to be under the curve in that area, right? So this is, for example, the 95% significance region is going to be these two tails, which is going to have 2.5%. So that means that this middle half is 95%, okay? And then this is the 5% significance region, right? Does that make sense? Okay. So what's going to happen is that you're going to, if you have an observed value, it's always going to be on this x-axis. If if you see a value here, what is that? What is that significant? What about a value here? No? Right, not significant, right? Okay, so that's the idea. Okay, so then how do I, so this is the standard normal, okay? This inverse normal, okay, is what? It's a function that we'll call phi minus 1, and it takes as input a probability, okay, and it tells you the x coordinate of where that probability is, kind of the area under the curve. Okay, so for example, negative x, if I take phi minus 1 of 0.025, what is that going to be? That's going to be, it's going to be the position on this axis where you know, the area of the curve before it is going to be 0.025, right? So you guys see how that's going to be negative x, right? What about this one? What is this one? This is going to be, it's going to be 0.9725, right? That's going to be x. What is that? That's because it's going to be this, it's going to be the point here where this whole area up until that point is going to be 9725, right? That's going to be 95% plus 2.5. That's 97.5, right? Does that make sense? Okay, so that's x. And so if y, which is going to be your observation, is less than phi minus 1 of alpha over 2, then where are you going to be? Let's say alpha is 0.05 in this case. On this axis, where are you going to be on this graph? You're going to be somewhere in this region, right? So you're going to be in the critical region, right? What about if you're greater than this value? What is that going to be? So this is, wait, there's a negative here. What's going on with that? So it's be greater than negative x, which is x, right? So you're going to be somewhere over here, right? Also in the critical region, okay? So alpha here is what? Like in the picture. Is it 0.25? Is it 0.25 or what is it? It's 0.05, right? Because this alpha, it's alpha over 2, right? So why is this alpha over 2? Because you have two tails, right? So the sum of them is 0.05, right? Okay, we'll be doing lots of examples of this, so don't worry. Like there'll be lots of examples in class and lots of examples in the next couple days and in the homework too. Okay, but that's what this phi minus 1 is. Okay, so just a couple. Okay, so that's what the inverse normal. So what is actually? Let me give you guys a bonus question. What is phi of minus x? So not phi minus 1, but phi of minus x. It's going to be, yeah, 0.025, right? Okay, so that's called inverse because basically it's like going the different directions, right? So inverse of a probability gives you the position on the x-axis. Phi of the position on the x-axis gives you a probability, okay? Okay, so here's some more properties of normal distributions. So if x is normally distributed, y is normally distributed. If you sum two normal distributions, what do you get? It's going to be normally distributed. The mean is going to be what? The sum of the two means, okay? And what's the variance going to be? The what? The sum of the two variances, okay? That's just a property of the normal distribution. What if you subtract two? You know, what if you subtract two normally distributed variables? The mean is going to be what? The difference, right? And what's the variance going to be? The sum. Did I make a typo here? No? Right, so it's kind of different because this is like a minus. Here you've got the minus, but here you've got the sum, right? Why is it the sum? Why is this not the minus? Huh? Why is this not a minus? Yeah, so it's like, yeah, basically variance associated with it, right? Okay. Let me actually show, let's revisit that. What is, if I have a variable a times x, this is a scalar, the mean is going to be a times the mean, right? And the variance is going to be a squared times times the variance, okay? So now, what if I combine this rule and this rule? Can I get this rule? How would that work? So what is like x minus y? What's another way to say that? X plus negative 1 times y, right? So what's it going to be? What's negative 1 times y? It's going to be normally distributed with a negative 1 times the mean, right? And what's the variance is going to be? The same variance, right? And so then you're going to get this rule, okay? Why am I spending so much time on this, okay? Because I can guarantee, well, actually, I hope not. I really hope not. But on the midterm, one of the most common mistakes is going to be from this, like turning this into a minus. So please don't let it happen again, okay? Okay, so now, what if I subtract the mean and divide by just basically the square root of the variance? What do I get? What do I get? If I subtract the mean, what do I get? So just this part, it would mean of 0, right? And then the variance would be whatever. Because when you subtract a constant, it doesn't affect it. Then if I divide by this, it's kind of like multiplying by 1 over this squared, right? And so then the variance would cancel. So you have a variance of 1. So this is what? Which one is this called? This is called a standard normal, okay? And this process of subtracting the mean and dividing by the variance is called a z-score, okay? Do you guys remember what we did when we did the data from class? What did we do? Remember we had the observation, okay? We subtracted the mean, 0.25, and then we divided by something, the square root of something, right? So that was exactly what a z-score is. And then we know that it follows the standard normal, right? And so why did we say that if it was greater than 2, it was significant? Because that's about 0.05, okay? Actually, if I go back to this, x is about actually 1.96. That's what x is. Okay, so that's what it's equivalent to. Okay. This thing here, chi-squared, okay, with 1 degree of freedom, that's approximately just the square of the normal distribution. So if you have a normally distributed random variable and you square it, actually if you have a standard normal distribution, standard normal variable, you square it, that'll follow something called chi-squared, okay? So chi-squared is approximately the square of the normal statistic test, right? If you look at a lot of the literature for hypothesis testing, they use chi-squares, okay? What do you lose when you square something? The sign, okay? So that's why, you lose some information, that the sign, but also what's the benefit of squaring it and losing the sign? Yeah?
Makes large things larger, small things
Well,
smaller.
that's what it actually does to the number. But I'm just talking about if these are equivalent, what's the kind of intuitive benefit of squaring something, right? Yeah, exactly. Like here, we have to deal with these multiple conditions and stuff like that. And then you've got this alpha over 2 thing they always have to remember. And when you square something, it'll always be positive, and so then you can compare it just to alpha, okay? So that's like that's why people use it. But what we'll show in class, actually, the sign, you actually lose something. But if you look at a lot of the literature, they'll be talking about chi-square test. But if you just take your z-scores and you square them, that's the same as a chi-square, okay? Okay, so far so good? Okay, so here's actually another couple things. So let's say this is if an event A occurs with probability PA, okay, and now I have n trials, which means that, let's say I'm flipping coins or whatever, and every time it turns up heads, it's probably PA. Then the number of times that it'll occur in n trials has approximately mean NPA, right? That makes sense, right? If you were doing n trials, let's say heads, you get 50% of the times. I do 100 trials, 100 coin tosses, I should get about 50, right? That's NPA, and this is the variance. It's going to be NPA times 1 minus PA, okay? Why is that? I mean, in stats 100, you derive that. It's not so important, okay? I mean, no, it is really important. I'm just saying this is just something that you have to just know, and you don't have to prove this in the exams. But basically, so this is the normal distribution, NPA, and this is the variance, okay? So now what if I want to measure what is the frequency of that? What is the frequency of the of that trials, which is going to be, I'm just writing it as PA with a hat. Okay, so PA is going to be whatever the true frequency is. PA hat is going to be what I'm observing in my data. Okay, so how do you, if I say that, let's say I get, I see out of 100 trials something happens 32 times. How do I get the formula? What's the frequency? This is a really easy question, actually. Huh? What is it? 0.32. How did you do that? Yeah, so you take the number of observations and you divide it by the number of trials, okay? What is dividing by a number? That's the same as multiplying by 1 over that number, okay? So then what's the distribution of PA hat? It's going to be whatever the distribution of NA is times 1 over NA, right? And so what happens? So what happens to the mean? The mean is going to be 1 over NA NPA times 1 over NA, 1 over N. What happens? This is going to, the N's cancel, right? And you end with PA, right? What happens to the variance? So what if I multiply NA times 1 over NA, 1 over N, what happens to the variance? It gets multiplied by 1 over N squared, okay? And so what do I get? I get 1 over N squared here on the denominator, and then what happens? So one of the N's cancel, okay? And I'm left with what? Just an N in the denominator, okay? So actually, what does that tell you? Like, what does this tell you? Like, if I'm computing frequencies, if I'm just collecting data and I basically compute frequencies, meaning that I look at how many times something occurs divided by the total, what does the mean tell me? That on average, what's going to happen? You're kind of getting the right answer, right? On average, your average, you're going to expect it to be around the true frequency, which is good, right? And what happens is you collect more and more data. Huh? Yeah, the variance around that is going to get smaller and smaller and smaller, okay? So actually, if you think about it, it really turns out that we're very lucky that the variances get multiplied by the number squared, okay? What if the variance was not multiplied by the number squared, it was just multiplied by that number? What would the variance be? It'd always be PA times 1 minus PA, right? And so then what would happen is we collect more and more data. Like, doesn't help. Collecting more and more data doesn't help, okay? So, I mean, I know this is kind of getting silly, but I'm just saying is that this is, if you think of our entire ability like the entire intuition of why we're saying more data is good, okay, is exactly, can be summed up in this equation right here, which is that the more data so there's some true parameters that you want to try to estimate from data, and the more data you collect, the variance around those estimates gets smaller and smaller, okay? So you can think of like our entire civilization is basically built on this. It's very important, okay? Okay. So a couple more factors. Correlation between the covariance between events A and B is PAB minus PAPB. You might have, and then there's something called the correlation, which is going to be this. It's going to be PAB minus PAPB divided by the variance of A and the variance of B, and that's called R, okay? That's called the correlation coefficient. People have heard that, R, okay? R squared is something that you see a lot. It's just this number squared, okay? People look at that a lot, okay? So this is just okay, so this is actually, so there are a couple more definitions. P-values, that's, actually we're going to give these examples. P-value threshold, null hypothesis, alternative hypothesis, and power. We're going to cover all of these. I'm just putting these definitions in the slides here, so it'll help you study for them. Okay, so there's also there's something in statistics people call type 1 error, type 2 error, right? Type 1 error is when those are called false positives, right? So if you're measuring significance, what's an example of when of a false positive or a type 1 error? So for example, let's say we're doing the computer science stay up late. Can someone explain to me what would be for that problem, what would be a false positive? It would be what? So it's basically the probability of declaring the effect significant under the null hypothesis. So it would be if people in the class only stayed up, people in the class are the same and each one of us have a 25% chance of staying up late, okay? But just by chance, there happened to be a bunch of those 25% people in the class, right? Just by chance. And let's say the significance level was 0.03, whatever, we would say, yes, they stay up later, okay? So that's called that would be a type 1 error, okay? What's the probability of a type 1 error? Always. Huh? Yeah, typically it's like the significance threshold, like 0.05. Okay, you actually set the threshold, right, in order to guarantee that your probability of a type 1 error is exactly alpha. Okay, that's how you set it. Type 2 error is called false negatives. Okay, what would be a false negative in the context of people staying up late? Yeah, I know it's like near the end of the class and you guys are getting tired, right? Okay.
People didn't want to raise their hand.
Huh?
People didn't want to raise their hand.
Oh yeah, people didn't want to raise their hand. So there's a reason, that's a bias, right? But actually the statistical reason could be as follows, which is that people in the class, for example, it might be that people are, let's say, 27% of them stay up late. And when we measured the data, we only saw like, 22 of them, and that just wasn't significant, right? Does that make sense? So either the effect could be small, or maybe 50% of them in principle stay up late, but we just happen to get all the ones that stay up early, right, in the class, right? So type 2 error is called false negative, and we're talking about that. It's going to be related to power. Okay, so actually this is a good place to stop. So what we're going to do, this is just a stats review, and what I didn't cover is what I meant to cover, which is how we're going to analyze DNA data. But we'll, because it's 3:48, we'll cover that tomorrow, okay? Wednesday.